Hello and welcome to the QEM Heroes webinar series. I'm Christine Wood and I serve as the Assistant Program Director for the Heroes Fellows Program at QEM. And for more than 30 years, QEM has been a national catalyst for STEM education transformation and research capacity building. Currently, the QEM network serves nearly 900 colleges and universities and reaches more than 8,000 individuals nationwide. This webinar is part of the HEROES initiative. The HEROES program brings together researchers with experience in the federal government to lend their expertise and support to the STEM research and education communities. Our fellows are here to provide tools and tips for navigating the funding landscape, developing STEM programs and partnerships, and improving talent retention in in-demand fields. We hope this series promotes engagement with our Heroes Fellows and provides valuable resources to our participants. During the webinar, we invite you to use the Q&A tool to ask questions. We'll address questions at the end of the presentation. And the webinar recordings and slides will be available in the QEM Resource Hub. By attending this webinar, you will be added to the QEM network and granted access to the Resource Hub. And today I'm happy to introduce our presenter. Dr. Yulia Goreva is a geochemist by training with a PhD from Caltech, specializing in earth and planetary sciences. She previously served as a scientist at the Smithsonian National Museum of Natural History and as a scientist technologist at NASA's Jet Propulsion Laboratory. And without further ado, I'd like to turn the floor over to Dr. Goreva.
Good morning or good afternoon, everybody. Thank you for being here. This webinar, if you were attending webinars of our of QM network, you saw that there is a variety of different presentations and a variety of different resources that are given during the seminars. I am going to continue the sort of education and starting a new research project or a new faculty or supporting undergraduate smaller research type of opportunities. So I'm gonna continue this line of introducing you to a niche science research project that may sound a little bit off stream or intimidating, but actually not, and where students can meaningfully be engaged at the beginning, when they just start learning about science, when they just start learning about how to do science and what kind of research you can start with them. So I'm going to talk today about meteorites. These are wonderful rocks that I call them poor man's spacecraft. This is the samples of the solar system that are delivered to Earth by nature. There are no robots, there are no exploration, no spacecrafts, and so forth. These are the rocks on the ground. So as a sort of front catch, I put this slide together for the three famous falls that change science. And falls, the meteorites roughly divided into falls and finds. Finds are the ones that you find on the ground, and falls, those are actually seen to hit the Earth. So if you've seen it, it means that has very, very little time, spent very little time on Earth. It just fell. It's very fresh and can start at that. So these are three very different falls. Chelyabinsk, only a few years ago in Russia, exploded at 30 kilometers altitude. The awesome thing about that bolide is that there are like almost any car in Russia has a dash cam. So it was filmed, and it was filmed from different angles at different times, and the entire history of the explosion can be reconstructed frame by frame. There is no crater left because it exploded at fairly low altitude, but still exploded in little pieces. But there is a lot of meteoritic material recovered after that. Then in the middle, Allende, found in Mexico. It's almost 2 tons. And this rock is amazing. I am going to talk about this type of meteorite. This is carbonaceous chondrite. They are rare, and the fact that there was 2 tons that fell, it gave a tremendous amount of material to scientists to learn about very early solar system. And on the right is Hoba in Namibia. And this is the largest meteorite ever found, and it was never moved because you can see that there's a theater was built around it. Uh, so the human would be, yeah, it's about like higher than the waist height, the size of it. Interesting thing about this rock, other than it's just very large, it survived the atmospheric entrance, is that it left almost no, despite the size, it left almost no crater. So we can, if you have questions, we can talk about that and hypotheses around that. But these are the three that are extremely science-changing meteorites. So what I cannot advance my, there you go. So what I'm going to talk about, it's not going to be very long. I'm going to talk about how meteorites form, their classification, a few of the main lessons that we learned from studying meteorites, and then what can be done to start a research project in this field. First, very grade school level, the terminology is a chain, not to be confused. Meteoroid is any solid object in space. It can be small, millimeter size, sub-millimeter is usually called dust, but millimeter size to kilometer scale. These are meteoroids. Meteors is what we see in the sky. So the meteor shower, it's basically what we see in a flight. As a meteoroid enters the atmosphere, it starts burning due to friction, and it starts shining. This is the streaks, and this is what we see. We see meteors. Once it falls on the ground and actually survives, that's the meteorite. And that's what I'm going to talk about. And a little fact here, answer that only 4% of meteoroids that enter the terrestrial atmosphere actually survive to become meteorites. Most of them either burn in the atmosphere or pretty much disintegrate. A good example is Tunguska meteorite. It was a huge explosion, a big meteorite, was a lot of damage, a lot of taiga forest laid down, big shock wave. There is virtually no material left. Origins. Almost all or vast majority of meteorites come from asteroid belt. Asteroid belt is a primary source of meteorites. It's this between Mars and Jupiter. So Mars here is in red, and this is Jupiter. I put this sort of a big point on asteroid belt because there's one body, the largest body in asteroid belt is Ceres. And it's actually classified as a planetesimal or small. It's a small body, so it's big enough to have its own classification. But it is an asteroid belt. It's the area where the gravity and pull and also from Jupiter did not allow for a big planet to form. So we have all these fragments on the orbit between Mars and Jupiter. We have all these rocky fragments flying around. Of course, some meteorites, rare ones, come not from asteroid belt, and most notably, we have lunar meteorites, and we have meteorites from Mars. I apologize for this picture. Kind of try to draw a cartoon and of how do we actually get them from asteroid to Earth, and kind of like kindergarten level cartoon. So usually meteoroids are kicked off from some larger asteroid, from asteroid belt by impact. So two bodies collide, pieces start flying out or eject, and they slowly start spiraling towards the sun. There are all kinds of different physics coming, and orbit reshaping, like Yarkovsky effect, for example, that shape the trajectory of this falling. And if we are lucky, this spiral towards the sun will cross terrestrial or the Earth trajectory, and then the meteoroid enters the Earth atmosphere and gets pulled. They enter at fairly high speed from 11 to 72, 75 kilometers per second. And because of that speed, that's where the friction starts, and friction hits the outer layer. And this is the streaks that you see in the sky when you see the shooting stars. Most of the rocks get fragmented. Most of meteorites were former meteoroids. They entered as one body and then they got fractured in the atmosphere at different heights. And then when they fall on the ground, it's not one single rock, with some exceptions like Hoba, but it's a strewn field. So it's kind of like a shower of fragments, pieces on the ground. Of false witnessed finds discovered later. I did talk about that. Where do they mainly come from? So meteorites fall all the time. In fact, it's estimated that every year the Earth gets about 40 tons of extraterrestrial material. Most of it is dust. The other most big part of it burns in the ground, in upper atmosphere, and still comes as like very small fragments, but some do reach Earth. Most of the area of Earth is ocean, so they end up in the ocean, but some on land. And of course, we look for meteorites in places where two things happen at the same time. One, it's easy to find them. And second, they are preserved. So if a meteorite fell a few thousand years ago, rain in the water in the rainforest pretty much will disintegrate it. If it's in a desert, whether it's icy desert or a dry desert, like a desert, there is a high chance it's going to be preserved. And that's where most of the science collection of meteorites is coming from. It's Antarctica, ice shields, dry, cold, perfect preservation conditions. Sahara and Namibia deserts, Australia, and Atacama Desert. So all deserty places, preservation and easy to find. In the desert, you have a dune. If you have a rock, there's a high chance it's a meteorite. In Antarctica, it's ice, it's blue or white, but anything that doesn't melt and not you is a meteorite. So I talked about this heat in the atmosphere. This heat produces the what calls fusion crust, and this is a beautiful rock. Actually, it has several things going here. You see the glossy surface. That's the one that is like 1 to 2 millimeters thick only. The bigger part of meteorite got burned, and this little crust, sort of like a crust of a bread, preserved what's inside. Actually, temperature inside the rock, the rock did not heat that much. There's certain evidence that the temperatures inside majority of meteorites never exceeded like much of like room temperature before they hit the ground. So there's a lot of science that is preserved inside, and in part because this fusion crust, this little crust was formed, and you can see the interior peeking over here in this corner. It's a little bit lighter, so that's under crust. This one is oriented. This is a nose cone. It's actually was where it was heading through the atmosphere, the orientation. And this is like this thumbprints, they called regmaglyphs. They're like depressions. They form from vortex ablation. And I brought, as a part of show and tell, I brought a little meteorite here. Let's see if you can see this. Okay, stop. Right, here you go. Christian, can you see this?
Yes, I can.
All right. So this is very similar little meteorite. Uh, it has it's fully enclosed in fusion crust, also very glossy, very black, nice, and it also has a stress fracture here. This piece of bigger meteoroid, but it also tried to get broken into at least two more pieces, but didn't quite make it. So there's a stress fracture that went halfway through, but never actually broke it apart. So this one is from Antarctica. All right, classification. The taxonomy of meteorites is based on three things: chemistry, mineralogy, and petrology, and that we can from which we can infer their history. So three things: chemistry, mineralogy, and petrology. So if you're a geologist, you know mineralogy, you know microscope, most likely you will be able to identify meteorites and possibly even roughly classify them without the sophisticated equipment. Most of us, when we talk about meteorite and you Google or ask a layperson, say like, well, what kind of meteorites are there? And they would say, oh, we have stony irons and irons. This is actually not really correct or not quite correct classification. The meteorites are classified or divided as differentiated and undifferentiated. These are two big groups. And undifferentiated, this chart I pulled from Johnson Space Center curation, astromaterials curation. And undifferentiated, they're also called primitive. So it's primitive and differentiated. Very simple. Primitive is the material that almost as it was when solar nebula was condensing 4.5 billion years ago, or over 4.5 billion years ago. And differentiated comes from bodies that were either big enough or hot enough to start partial melting, sort of the beginning of the core formation and core and mantle formation, like on Earth. So you have undifferentiated and differentiated. Undifferentiated are chondrites, and chondrites, the word comes from chonders, which is the kind of this little rounded objects. The most fascinating thing about chondrules is that there is no astrophysical model that would have or could have predicted their existence if we actually didn't see them in the hand specimens. There is the mechanism of chondrule formation is still debated. There are several proposed, there are some leading, but if we didn't have meteorites, if we didn't identify them as meteorites, we would have never predicted that this kind of things would form. And I'll show a picture a little bit later on. And differentiated, these are achondrites, and stony irons and irons. Iron, of course, is a former presumably former core of a small planetesimal or broken apart small body in asteroid belt. Stony irons are sort of in between, and achondrites are igneous materials, very similar to, or somewhat similar to terrestrial mantle or crust. So this is the chondrite. This is a piece of Allende that I mentioned that's from Mexico. And I'm not going to get into details of classification, but I just want you to look at this picture and notice three things, three big categories. We have this round, like almost perfect droplet-like round objects. These are chondrules. There is this gray mass. It's actually almost black. It has a lot of, that's why it calls carbonaceous chondrite. It has a lot of almost primitive carbon and organics and all kinds of more complex carbon compounds. And then we have these irregular white inclusions. And those are, to me at least, are the most fascinating. They're called calcium from chemistry. They are called calcium aluminum rich inclusions, or CAI. CAIs are the oldest objects of our solar system. These are the refractory inclusions that were formed, the first formed when the solar nebula was condensing solid matter out of dust and gas. Achondrites, this is from differentiated words, and now the scientists know enough to even assign some of the groups of achondrites to specific planets. So we know that SNC group comes from the name of three initial Martian meteorites, Shergoti, Nakla, and Cassini. They come from Mars. HED, Howardite, Eucrite, Digenite type stones come from asteroid 4 Vesta. Of course, we have lunar meteorites. We have a whole group of which calls Uralite, which all come from this. We know that it come from the same body. This is based on oxygen isotope systematics, because the oxygens fractionate in a way that preserve relationship between oxygen isotopes unique to a planetary body that the rocks are coming from. So everything on Earth plots in the three isotope oxygen system on Earth. Everything plots on a line, on one line. And the Martian meteorites also all fall on one line. It just offset from the terrestrial and so forth. And there are some achondrites that we don't know that they come from one place, from one body, but we don't know which one. Iron and stony iron. So on the left is a iron meteorite, so presumably core of a destroyed planetesimal. What you see the streaks here is called Widmanstatten pattern. It's a lineation from interlocking iron and nickel rich crystals. You cannot really see this kind of pattern in a rock. If you just saw it, you have to acid etch it to see it. But it's present with a different thickness, present in almost every single iron meteorite. This kind of pattern forms when the cooling rates are extremely slow. That's another point for it being part of the core. On the right here is a palisade. That's stony iron, and the person here it's Marvin Kilgore, one of the meteorite dealers, who is very friendly to scientists and science research and meteorite research. We've got a lot of specimens from him directly, and he is with this slice. This is only a slice. It's this about maybe like a couple of inches thick of Fukang palisade. And Marvin brought it from China. It's a huge, beautiful rock. And this white part is metal, just like this, like iron meteorite metal. And the yellow-green are olivines, or olivine clusters. So it's absolutely gorgeous, and presumably palisades come from this core mantle boundary of a broken up planetesimal. So what do actually we learn about from meteorites? Plenty. We have organic materials and carbonaceous chondrites. We have refractory materials and carbonaceous chondrites. Those white inclusions that I showed, this CI, calcium aluminum rich, even the very first, you imagine dust and gas outdropses and cools down, the material that cools down kind of starts close to the sun. The refractory things condense first into solids, and then further and further and further, sort of analogous to a solar system. You have rocky planets closer to the sun, and then gas giants further out, the cooler temperatures. So it all started with condensates that are very, very small. And the first ones to condense were these calcium aluminum rich inclusions, 4.5, almost 57 billion years old. So it's the oldest objects in our solar system that we have and we can study. I think this is actually absolutely fascinating. But if you think that is old, the carbonaceous chondrites and it's some ordinary chondrites as well, they have even older parts in that, and dust particles that are not from our solar system. Some of them are part of the nearby supernova explosion. Some of them just traveled in the interstellar medium before falling into or getting absorbed by the solar nebula. And there are four main categories that scientists identified. There are silicon carbide grains, spinel and corundum, graphite, and actually micro diamonds, and very, very rare, recently discovered silicates, rare because they barely survive or very rarely survive an interstellar environment. But we know that this kind of materials, from their isotopic signatures, we know that they could not have formed uh, uh, from our sun, our sun or our star generation stars. So they got to come from somewhere else. And of course, water, plenty of water and carbonaceous chondrites. Of course, it's not water droplets. It's trapped in minerals, but we have almost 18% of water in carbonaceous chondrites and organics, amino acids, nucleobases, all kinds of compounds were found in carbonaceous chondrites. And so that suggests to many scientists that with all that rain of meteoritic material, who knows, maybe that beginning of life on Earth actually was brought as building blocks were brought by cometary or meteoritic materials. So I am perfectly on time. Let's talk about what students, undergraduate students, or maybe young faculty can do start with geology background, geology mineralogy background can do start a meteorite project. It's not that difficult. First, you have to, of course, like in any research, you have to define your research questions. And here I put, of course, not exhaustive, but I kind of put large groups of themes of research questions. It's classification, geochemistry, petrology, cosmochemistry, chronology, needed big labs for that, so a lot of collaboration and public outreach, education, exhibit curation, citizen science. This is something that any research institution that has a passion for meteorite or has students that have passion for meteorites can actually do. I want to call out classification here as well. There is a certain protocol and nomenclature committee that approves new meteorites. And there are several US institutions that identify meteorites and classify them, including Arizona State and University of Arizona, WashU, UCLA, so number. But that number actually falling. So there are fewer, mostly because of the funding. There are fewer and fewer U.S. institutions that do proper classification. So I won't be surprised if there are more sort of a the hotspot labs or groups. I will start focusing on that because there is definitely a need for all people, like people coming to me still with the rock and say, oh, is this is a meteorite? So we need to identify them and we need to classify them in order to formally be accepted as a new meteorite by the nomenclature committee. Uh, where do you get data? Where you get science? And where do you publish? So there is a meteoritical bulletin that is sort of joint publication by Johnson Space Center and Smithsonian. It's an official registry of all named meteorites. You can search it by name, type, full find, country, year, and where the type specimen located. Astromaterials at Johnson Space Center, they curate a lot of rocks. The Antarctic meteorites, almost all of them in Houston, lunar meteorites, cosmic dust, stardust. This is the Stardust is a space mission. It's a return that returned pieces of a comet. It kind of flew through the cometary tail and collected little particles and came back to Earth. And now JC is curating that material and loans it to researchers for study. Genesis is another space mission that is a return of the solar wind. I was involved in that mission. The solar wind are energetic particles, so they're much harder collectors that kind of collected the implanted solar flare particles, and it was returned to Earth as well. So you can request the samples as a researcher. Meteoritical, and it's any researcher in a U.S. institution can request meteorite samples for free. All you need to do is to submit a small proposal with your research. Of course, if your research is non-destructive, like you need to study rock or thin section, or maybe do mapping or chemical mapping, or introduce some AI tools to scan for chondrules and their characteristics. You can request samples from GSC or Smithsonian, and there is also a lab in London. And it's completely free, but it is going through review. Every proposal goes through review, of course. Meteoritics and Planetary Science is the main journal. Almost all meteorite research is published in Meteoritics. ANSMET, Antarctic Search for Meteorite, that's the Antarctic research program that I mentioned. It's based in Case Western University. So look through their database. International Meteorite Collectors Association, beautiful map base, and where you can find whether the dealer that you may be buying a meteorite from is legitimate. The classification standards are there, and the market data. And samples for Hayabusa and OSIRIS-REx, which are asteroid samples from sample return. Not quite meteorite, but it is. Those are still samples of the asteroid materials or meteoroid materials. So you also can request the samples or some samples for the study if you have justified research. Analytical techniques, this is where most of work is done because these are samples in hand. And if you're a smaller research or mostly educational institution, you don't have access to secondarization mass spectrometers or thermal ionization mass spectrometers or time of flight mass specs. These are like big guns. These are big labs. And in fact, there are only a handful of laboratories that have this instrumentation and do meteorite research. So if your research is headed towards chronology, towards dating and isotopic work, you have to build collaboration. But optical petrographic microscopy, it's accessible almost to everybody. Almost any university would have a microscope. So you're teaching students how to look at thin sections or thick sections, how to identify parts of meteorites, how to identify even some rough chemical composition from petrologic thin sections. This is this is available. It's available almost at any university. So the students can do that. This is the lowest barrier. The scanning electron microscope. This is a little bit higher up, but also becoming more and more available at the universities. If your department, which is maybe like geology or earth sciences department, doesn't have scanning electron microscopy, material science should have one, or almost any university somewhere may have the scanning electron microscopy. And sort of in between these big guns and microscopy is electron microprobe, which is a very fancy scanning electron microscope that actually can measure chemistry in a spot, in place, and inductively coupled plasma mass spectrometry, XRF, and so forth. So this is sort of like the tools that you need to address different parts of meteorite study. Right. So acquiring samples, institutional loans, as I mentioned, Smithsonian Natural History Museum, Natural History Museum, London, NASA, Johnson Space Center, free samples to researchers, thousands of meteorite of Antarctic meteorites. To get a sample of Mars is highly competitive and very difficult. We have thousands, tens of thousands of specimens of ordinary chondrites, which are not that ordinary, but just more common. But there are tens of thousands of specimens of ordinary chondrites, and there's quite a bit of carbonaceous chondrites as well. So submit a proposal describing your method's goals, can be educational goals, and get the samples. You can purchase samples. You can purchase meteorites from vetted dealers like Marvin Kilgore. I don't want to sort of product place him, but I just worked with him for several years. And there are wonderful dealers that do support research. They do sell meteorites. This is their business, but they also would lend or give pieces of rocks to researchers if you ask them. Fieldwork, unspent Antarctica for 50 years, except for a 3-year gap. I think they had every single year this team goes to Antarctica to collect meteorites on ice. That's the Johnson Space Center and Smithsonian. Or chase the observed falls. There are several resources, online resources, where people report sightings of meteors and meteorites. Once you have one fall observed from several places, you do triangulation, and you can actually narrow down location where the sample hit the ground. Yes, there will be dealers, but there will be lay people or scientists there as well. So I've done that. I went to chase meteorites in New Mexico, in Arizona, and yeah, I have a few meteorites that I found myself after seeing streaks in the sky, and yeah, after seeing it fall. But main thing, collaboration. A partner with a curator or PI who has access to meteorites, and more importantly, access to the lab, to the equipment. There's plenty of work that can be done on meteorites that students can be trained to do, that can do themselves and actually have a meaningful research project. But you do have to have a collaboration for chronology, for really detailed chemistry. A Meteorological Society. This is a society that all meteorite study people belong to. There are annual meetings. I think they have alternate 2 years in a row in US, one abroad. LPC is always in Houston, Lunar and Planetary Science Conference. So MedSoc, that's nomenclature committee. That's the pathway to actually name a new meteorite, citizen science. And there are plenty of open access sources of both data, information, and key papers. So if you're a geologist or earth scientist, you know meteorology, you know geology, your students want to use their geology skills on rocks that actually come from another planet or from a small body like an asteroid belt. Uh, Start small. Classification. Get them classify a known meteorite. Replicate a published analysis. Get them to build skills before actually build projects. And maybe once they finish their undergraduate, they go to grad school to actually to become meteorite scientists. All right, this is a busy slide. I'm not going go through that. It's probably not exhaustive, but I pulled all the grant funding opportunities that I could think of that in one way or another support study of meteorites or support students or researchers, including starting and young researchers to study meteorites. There are big guns like roses, for example, from NASA, but there are much more lower barrier or smaller grants that can be applied for to start or to support existing students or new faculty members at your institution. So I'm just going to leave it. You have an access to the all presentations of our series. So this is something to explore if you're interested on your own. All right, so and I will finish with our traditional codes on the last slide. On the left is I took this picture. It's not me, but I took this picture in Antarctica during one of the Ansmith expeditions. This is a friend of mine and dear colleague, Carrie Corrigan. She's a curator at the Smithsonian Natural History Museum. She's a curator of meteorites at the Smithsonian. And here she is with her skidoo, with her snowmobile, with fairly large find here, a large meteorite. She's happy because most of the rocks that we find in Antarctica are sort of below the fist side. This is a big specimen. And then in the back over here, you can see another member of our team, also with their skidoo. I think since he's on foot or she's on foot, they probably found or saw another suspect of meteorite. So you can see the spacing. There were four of us only. So we were grooming this big ice field looking for meteorites. And here's Carrie with one of them. And Christine, can you take over if there are any questions? And I think I'm done.
Thanks, Julia, that for a fascinating talk. The floor is open for questions. You can either use the Q&A box or you can raise your hand to be taken off mute. And I'll remind folks that these QR codes lead you to the QEM events page where you can register directly for upcoming webinars, and Heroes webpage where you can learn about our Heroes cohort, and the webinar feedback form where we collect your feedback for the webinars. Questions?
It's either completely out of the field of interest or people are stunned. I hope you're stunned.
Not a question, but just wanted to say thanks to Yulia. You give wonderful talks from Cary Hall.
Thank you, Carrie.
All right, folks, if there are no questions, we will conclude. And I want to thank you for attending our webinar series and thank Julia again for a fascinating talk on meteorites and meteorite projects. Thank you very much. And we'll see you tomorrow at another Heroes webinar.
Thank you all. Thank you for coming.